Welcome to Divcasts from the University of Chicago Divinity School. For more of our podcasts and information about our terms of use, please see our website, divinity.uchicago.edu/podcasts.
Good afternoon. My name is Margaret M. Mitchell. I'm the Dean of the Divinity School and Professor of New Testament and Early Christian Literature. I am very pleased to welcome you to the 2014 John Nuveen Lecture. The John Nuveen Lecture was established in 1972 by the Baptist Theological Union, which is meeting here today under the leadership of its president, Larry Greenfield, in order to provide an annual occasion, the lectureship, that is, at which a distinguished member of the faculty of the University of Chicago lectures at the Divinity School on some aspect of her or his current research. John Nuveen was one of Chicago's most important and influential business and civic leaders. He had deep ties to the university, and he served as a trustee of the Baptist Theological Union. The BTU is a most valued partner to the Divinity School's mission of excellence in the academic study of religion. May I ask the BTU members present please to stand and be recognized? Phyllis Tessieri, Jeffrey Tyson, Don Musser, also an alum of the Divinity School, Larry Greenfield, also an alum of the Divinity School, Joe Price, also an alum of the Divinity School. Whom did I miss? Oh, Robert Schlurb. Robert Schlurb, BTU trustee and dear friend of the Divinity School. So thank you, dear friends, for all that you do to support our work in so many ways. We just had a marvelous meeting downstairs and lots of interesting conversation. So it's my pleasure to introduce our speaker, Donald G. York, the Horace B. Horton Professor of Astronomy and Astrophysics in the Department of Astronomy and Astrophysics and the Enrico Fermi Institute and the college. Professor York holds the Bachelor of Science degree in physics from the Massachusetts Institute of Technology and the PhD in astrophysics from the University of Chicago. Among a variety of appointments and service, he was research astronomer on the Copernicus satellite project at Princeton University from 1970 to 1982. Professor York uses a variety of orbiting and ground-based telescopes to study the interstellar medium, that is, the rarefied dust and gas in space, to learn about the origins of the elements, the galaxy formation, and quasars. He was the founding director of the Sloan Digital Sky Survey, a collaboration of 13 institutions and 200 astronomers around the world that in the year 2000 began conducting the largest census ever taken of the sky. He was also the founding director of Apache Point Observatory in 1983, home to the Sloan Project. The initial survey was completed in 2008, but continues to do innovative surveys with many more partners having joined. York also is the founder of the Chicago Public Schools University of Chicago Internet Project. The project focuses on producing a sustainable internet culture in public schools in the neighborhoods surrounding the University of Chicago. Research in Professor York's group focuses on diffuse material in our universe. Included in the focus are the origins of intergalactic material, the origins of elements in high redshift galaxies, and interstellar material in the disk and halo of the large Magellanic Cloud and the small Magellanic Cloud, the two closest star-forming galaxies. Progress in all these fields is closely tied to progress in understanding interstellar gas and dust in the Milky Way galaxy. Professor York is also interested in the relationship between science and religion. Among other things, having taught a course with Professor William Schweiker of our faculty, a course called Big Problems 23000, Cosmos and Conscience, Looking for Ourselves Elsewhere. I will say that I am secretly hoping that the lecture today will give us a glimpse into that fantastic course of which I've heard so much. The title of Professor York's lecture, the 2014 John Nuveen lecture, is It's Not the Heat, It's the Humility, The Limits of Knowledge. Please join me in welcoming our distinguished colleague and speaker. Dr. York.
Thank you very much. I want to talk to you this afternoon about the limits of knowledge, and I want to use my experience and knowledge of astronomy to do that. In this field, of course, there are truly age-old questions. It's not like chemistry where somebody 500 years ago would, you really couldn't look into the solutions and ask questions about it. It's not that way with the universe. Any 14-year-old, even in ancient times, could ask deep questions. What is the universe made of? Are the stars like the sun? Does the earth move? They only have 5 words, and yet they're extremely deep questions. It took hundreds of years for mankind to answer even the few questions that have been answered. There are just things that cannot be known at a given time in history, and the limits that we now know of that hindered people in the past should make us humble about our own confidence in what we know today. I'll tell a few different stories to emphasize first that new facts come up from time to time that completely change our view of the universe, to emphasize the crucial impact of technology driven by commercial and military activity, to discovery in astronomy, and finally, the shift from pride to humility over and over again. Just to give you a preview so you won't get hit too hard when they come up, I'll talk about some things that some of you know about, the Galileo and the parallax, the measurement of time, Kant's discovery of the expanse of the universe, Fraunhofer and Orphan and his enormous contributions to knowledge in the 19th century, the story of 2 telescopes, and the advent of what we call multi-wavelength astronomy, new eyes on the universe. The title may strike some of you as very non-University of Chicago. It's not original. It's not a direct quote. The quote does not make sense, and the tagline is absurd. Most of us think our ability to gain knowledge is unfettered. That's why the universe exists. Calvin says, God put me on earth to accomplish a certain number of things. Right now, I'm so far behind, I will never die. The quote is from Yogi Berra, and the reason it's not a direct quote is because I didn't want to have ain't all over your webpage. The actual quote is, of course, it ain't the heat, it's the humility. I heard this quoted while watching the World Cup being played in the jungles of Brazil last summer. Everyone thought only the Brazilians had a chance of getting through the humidity in the jungle. I was shocked by the nonsensical statement from the broadcaster, but then I realized it was completely appropriate to the topic that I was already thinking about. Our new Dean of Physical Sciences, Rocky Kolb, former head of astronomy and astrophysics, recently published a book entitled Blind Watchers of the Sky, emphasizing the fact, also pointed out in one of the quotes by Yogi Berra, that one has to be careful when you do not know where you're going because you might not get there. Astronomy is defined by those who do not know where they are going. I cannot speak for other fields, but the biggest questions in astronomy have more than one possible answer, given the scarcity of our knowledge. Most scientists could give a talk on this subject, but only in their own fields. It's a very scary fact that most of us realize the limits on knowledge in our own fields, that we act as if experts in other fields have all their answers in order. I can't further comment on that, but I do know the limits in astronomy, and that's the book from which I will take my text this evening. I'll take some of Rocky's stories to a more practical level involving the instruments that astronomers use. You will hear a few twists and turns on the intellectual side, repetitious of what you learned in 4th grade. The heat of the discussions around the nature of the universe has been most intense, just as were the well-known discussions around the emergence on the intellectual side of the Big Bang, dark matter, dark energy in the 20th century. But my stories are seldom told, and they should make us most humble as to what we understand about the universe and about the possibilities of ever learning the grandest part of the universe, namely its origin. On the intellectual side, most of you know the stories of Copernicus, Galileo, and Tycho. The story unfolded between 1543, when Copernicus died, and 1610, when Galileo first looked through a telescope at the sky. He published his first results in a famous book called Sidereus Nuncius, proving to himself that the Earth goes around the sun. Since the dawn of history, of course, humans have tried to understand the heavens around them. The record of this appears in many cultures over a period of 8,000 years, as shown by the famous relatively late structure at Stonehenge, which most of you know about, and right here at home, these shadow poles in Cahokia Mountains, which is only a few hundred miles away. Obviously, the cultures were quite different, but this is universal. People have been trying to figure out basically what the tilt of the Earth is for thousands of years. But the pointing of an accidentally discovered telescope at the heavens completely changed our view of the universe and of ourselves. Many myths were created before the telescope was invented, some based on solid observations, but incorrect interpretation. Galileo laid the basis for removing this myth and his observations with the use of the telescope. A long-standing question was whether the Earth orbited the sun, for instance. This goes back to your 4th grade. This is the little telescope that he used. It has a 2-inch diameter. It's on the right, and on the left, on your right, rather, is the telescope that Newton built 100 years later, 80 years later, which I will talk about in just a minute. First, Galileo discovered the craters on the moon. Galileo was a Renaissance man. His father was a Renaissance man, and he knew about the new art of chiaroscuro, shadow painting. So he immediately realized that the high points where the glint of the sun was out of place on the moon was mountaintops reflecting the light, and the surface of the moon was not perfect, as Aristotle had claimed for so many years. Of course, Aristotle projected that idea to the whole universe. Everything was perfect beyond the sphere of the moon and was spherical in all aspects. Some of you may know the story of the spherical cow. That came from Aristotle. He also found the moons of Jupiter and challenged the view that the Earth was fixed, that other bodies in the solar system move around it. It's incredible to realize that the heated discussions about which we all learned in school could revolve around a simple summary question: does the Earth move? As it turns out, it was over 100 years before scientists understood that the answer was yes. But the best argument at the time, the accidental discovery of an effect called aberration of starlight, which was a little hard for most non-intellectuals to understand, did not convince most people. The world concurred only 220 years after Galileo's first observations, when the first parallax of a star was measured. I want this to be an interactive lecture, so I want you all to hold your thumb up like this, okay? And close one eye. Look at your thumb and notice what's behind it, and then just close the other eye, switch back and forth. It's okay to do this several times. You can do it at home. It won't hurt. Your thumb moved or appeared to move. The same thing happens when the Earth is on one side of its orbit around the sun. And if you look at a star, you notice that the stars behind it are in a certain position. When the Earth is on the other side of the sun, 6 months later, you look at the same stars, and you see it has a different set of stars behind it, or a slightly different position with respect to the background stars. This effect is called parallax, and it was very well known in the 17th century. In fact, it was the absence of parallax in stellar motions that led most to insist that the Earth did not go around the sun, but vice versa. The heat and disrespect famously got turned up pretty high on this one. How could a scientist not recognize that a strong prediction of his theory did not come true? The fallacy was that the distance to the stars was unknown, unknowable, and much larger than anyone could imagine. The larger was the space of the stars, the less the amplitude of the parallax effect. The instrument necessary to measure the small angles simply did not exist for 228 years. It could not be proven that the Earth moves or that it stands still. In recent times, Nobel physicist T.D. Lee accepted the Pope's apology for the rude treatment by the Church of science and of Galileo. Lee said it was true that no one could tell for sure that the Earth moved, but it was ambiguous and there was no rational reason for the Pope to deny the possibility. The truth is that so much other cultural baggage was created by the days before Galileo, partly based on personal pride, that a series of accidental discoveries made by non-professionals were necessary to reveal our current position on the nature of the universe. These have stretched over the full 400 years. The story of the parallax is one example. Similar stories can be built around more complicated questions. What are the shining points of light in the night sky, even without talking about stars? How big is their realm? What are they made of? Are they made of the same elements that we know of on Earth? Well, it's complicated because, of course, that last question would mean different things to different people at different times. In ancient times, the elements that you were asking about would be earth, fire, air, and water. By 1800, you might be thinking about nitrogen, oxygen, hydrogen, and silicon. By 1982, the context would have changed to quarks and electrons. And over the years, even the issue of whether the elements were tangible or rather indirect forces and field versus particles. The gravitational force, the electromagnetic force, the strong force, and the weak force came to be. We now understand that these four forces are the true operational sculptors of the universe. The path through this labyrinth of knowledge was tenuous. The players did not know where they were going, and they did not realize what they were finding. Luckily, knowledge is not poisonous, but the heat and the arguments based on incomplete knowledge and on presupposition was intense. Many did not have the necessary humility to allow for the possibility of things not being according to the common view. Kepler and Newton were both somewhat apolitical beings who managed to keep themselves apart from the common view. They had time and uninterrupted leisure to reconstruct the universe. Kepler, by reducing Brahe's observations of the planets, and from it he derived a set of rules that the planets seemed to observe as they went around the sun. Newton took the time to derive these laws from first principles, from pure thought, using mathematics, and his assumption that the laws of gravity were universal. As a student, he went far beyond the facts and created a world that explained much of what was known about the universe for 230 years, until general relativity came into our consciousness. Take note of that number. I've used it twice now, 200 years. Today, we're much more sophisticated. This is an artist's conception of one of the big new telescopes. This is called the Giant Magellan Telescope. University of Chicago is a partner in this telescope. We've gone from the 2 inches of Galileo to current 400-inch behemoths to this kind of telescope, which has an effective area of effective diameter of 1,600 inches, or 133 feet. And it has a light gathering power 1 billion times what Galileo had. How did this happen? Why this enormous increase in potential of gaining knowledge? What I'm going to tell you is mostly by cultural accident. Curious people were needed just to take an inventory of what was in the heavens. And the more telescopes there were, the more people appeared to take that inventory. At first, all they found were 2 types of objects: point sources and fuzzy patches, and that's all they could talk about. Evidently, all at one distance, painted on the sphere of the sky, as Aristotle had advocated. It was clear that there was much more to be learned, that bigger telescopes were going to be necessary. There was a very large discussion over resolution and how sharply one could discern the images. Lots of pictures that were drawn. If you look at them today, it was clear that they were building their minds into the pictures. Very strange. Men of means, businessmen, some mathematicians made improvements in gathering light, but at the expense of building albatrosses that had no future. I won't explain why, but this telescope has an effective area, a very effective diameter of about 4 inches. It's 160 feet long, and it was just what you had to do to get decent images. Of course, there were probably only 4 people in the world who could use it. You could imagine what the wind would do to it, how it would flex, and so forth and so on. This was a dead end, as Newton liked to point out. Now, I just want to say that I'm going to use the word men a lot. There were women involved with the intellectual discussion that was going on. Molière wrote a famous play on the subject. But I'm talking mainly about technology, and as far as I know, that was all men. So I'm going to use that word as I go through this. This problem, this enormous albatross, was one of the reasons that smart men argued over whether lenses or mirrors, that is, reflecting telescopes or refracting telescopes, were what was going to be needed to go to newer, deeper understandings of the universe. And the arguments between the advocates of both sides were quite intense. No humility involved. Both lenses and mirrors, as they could be built in the 1680s, produced aberrations that kept point sources from being points. That is, as small as possible, given the limits of the atmosphere. Even the simple technical issue generated much heat. The great Newton categorically asserted that only reflecting optics could be successfully incorporated into larger telescopes needed to allow the deep views of the universe. However, despite his intelligence and intellectual power, acceptable solutions to both kinds of aberrations, refracting and reflecting, were found. By 1830, both lenses and mirrors found applications in excellent telescopes up to 30 inches in size. Again, there's the number 200. It took about 200 years for the optics of telescopes to mature. Then there was the issue of how to point the instruments, as they had to be changed in position continuously because the stars appeared to drift across the sky during the night. Or maybe it was because the Earth was rotating. Nobody knew at that time. Rich men, many industrialists who made their money during the Industrial Revolution, made telescopes with weight-driven motion contraptions, which gave way to motors and better mounting techniques. And precise clocks were necessary. These came from the famous development of the chronometer, built to keep British ships from going off course on their long journeys across the Atlantic. There are two kind of interesting sidelights here, and I tell them they're curious and interesting, but also I will emphasize with them when I'm finished here how this completely commercially driven enterprise or purpose turned out to be one of the great advances for astronomy. This is Jantar Mantar, built in the early 18th century in Jaipur, India. It's full of large instruments. All these structures have some purpose. The main and most precise instrument is this one, which was the last one built. You'll notice in the center of the picture in the background you can see people, so that gives you the scale. This enormous wall is casting a shadow on the white arc, and the white arc, it has little marks along it. Okay? And with this, you could tell time with an accuracy of about 2 seconds. Now, it turns out, for the kind of journeys that people made on their commercial ship trips across the Atlantic or around to the east, that kind of precision was all you needed. Of course, the problem was that you couldn't count on your ship always having clear skies. So what do you do when the ship doesn't have clear skies and you can't use the stars? This precision was adequate, but of course it's a little hard to put it on a ship. The British government set out a prize for an accurate timing technique that would be applicable to navigation. A clockmaker succeeded around 1875, though in a rather brash scandal he never got his prize. The famous astronomers thought they were the ones who were going to figure out how to tell time accurately, and they kept him from getting his reward. And again, a little bit detail here. There's a hill in Edinburgh called Calton Hill. It has a city observatory. This is one of the instruments there. It's since been replaced by a better instrument. But this is called a transit instrument. You can see there's a gray slit that can be opened. The telescope cannot move sideways. It just sits there. You can tilt it up and down. And as stars cross in front, you can measure exactly when they reach an apex and tell time in that way. So they would watch the stars go by, and when a certain star went by, they would make a mark on a recorder. They would then set this clock. This was called the politician's clock. It had one face facing inside the observatory, so the astronomers could set it, as they told time by the stars, and another face looking out the other way, which is why it's called the politician's clock. Toward Nelson's tower. Nelson, of course, is Vice Admiral Horatio Nelson, who was killed in the Battle of Trafalgar in 1805. This tower was built to commemorate him in that battle. And you'll notice, kind of interestingly, it merges right well with my story, that it's an inverted telescope. You can imagine Horatio looking out with his collapsible telescope. That's what the shape of this is. Again, a testimony to the fact that commercial military uses were the main uses of telescopes, much to the benefit of astronomy. Every day at about 1 p.m., the time, a time precisely known from the politician's clock, which could be seen from this tower. A ball was dropped from the tower that could be seen from the ships in the Firth of Forth, which is the body of water behind me in this picture. They set their chronometers by the fall of the clock at exactly the time that had been agreed to, and they set it for the last time, and then they sailed off into the ocean, knowing that they would have accurate navigation to North America, the Far East, or wherever they wanted to go. These newly improved clocks were used, starting in the early 19th century, to drive telescopes very precisely so that they could track the stars before electronic guiding systems existed. One example of the great boon to astronomy of commercial activities that had nothing to do with astronomy. As other examples of technology came to the benefit of astronomy, rich regions interested in natural knowledge supported astronomers and artisans in these pursuits, helping them to apply the technologies. A new level of instrument quality was reached by Joseph Fraunhofer. Orphaned at an early age, plucked from a fire at his orphanage by an industrialist, and mentored to become the best glassmaker in the world. providing by himself or through his company or through those he trained the glass for most of the world's telescopes through the year 1900. Again, the heat over good optics was intense, literally. And humility was certainly lacking, as making a good glass was a trade secret, over which employees had to sign non-disclosure agreements so the secret could not get out. You might guess what the secret was, but it's so simple that you wouldn't even call it a secret. The secret was that stirring the molten glass when it was hot kept the lead from settling to the bottom so that you could get a uniform mirror. The making of adequate lenses, incidentally, was also a trade secret, kept in particular families for many years. So it was with the prescription of polishing proper mirrors. You had to polish them and coat them. That was also a trade secret. I don't think the actual way of doing it was published until around 1920. The technology of excellent telescopes was, after all, about business. Rich men with toys, military men with telescopes for navigation, all of these far exceeded the number of telescopes built for astronomy. Now back to Fraunhofer, there are numerous single threads in the blanket of history, which if plucked out would have cut off knowledge of the universe for years. What if Fraunhofer had died in that fire in which he was trapped as a youth? It was Fraunhofer who made the two telescopes that first measured the parallax, which finally proved that Galileo was right. The Earth did move. And it was Fraunhofer who showed that the continuous rainbow of light in the spectrum of the sun was broken up into hundreds of thin black lines. The rainbow colors were known for years, starting with Newton. But the fact that there were black lines across the spectrum was first found by Fraunhofer. This discovery led to spectral analysis and the understanding late in the 19th century that the stars were made of the same stuff as Earth. This was an enormous breakthrough. Of course, there was a twist. This is the periodic table of the elements, the 92 stable elements. You're all acquainted with it. This is the astronomer's periodic table. We didn't know that hydrogen was the only thing in the universe. And I was thinking this week about this and wondered if the complexity of the periodic table fit with people's ideas about how complex the universe is. Right? And when they found out that the simplest atom is actually the basis for the whole universe, it must have been a little bit of a shock. Now, trained scientists finally got into the game. It was Bessel of Bessel function fame who figured out that the structures that made the best instruments still have flaws. Flexure in the instruments, irregularities of motion due to wind, having the telescope at poor sites where the atmosphere disturbed the images. All these effects had to be corrected, and it didn't matter how well you built the telescope. To make the first published measurement of parallax, he had to calculate corrections to all such effects. The world's best instruments were not adequate to the needs of astronomy, but they were good enough to correct. 10 years after this success, Bessel claimed, in paraphrase, all telescopes are built twice, once by the craftsman who works the steel and brass, and a second time by the astronomer who corrects the tiny errors. Accidents continued to drive the progress of knowledge. Accidents fostered by ever-improving technology, but not things done for the sake of technology, but things created by the demand of society for better products, better trains, more jobs, more money. Sounds a lot like modern times. Now, as the facts grew and the technologies got better and better, Immanuel Kant, of all people, in 1755, took it upon himself to interpret the simple fact that everything in the skies could be grouped as either points of light or fuzzy patches. This was clear from the notebooks of the astronomers, but he puzzled on this. I believe this was before he became a well-known theologian. Yeah, I learned that from Bill. If you look at galaxies today, the kind of things you see in the Hubble Space Telescope, it'd be hard to imagine actually seeing what these astronomers saw in their telescopes 200 years ago. This amazing structure with dust lanes across the center projected onto the background, a big ball of light in the middle, lots of stars scattered around the outside in the disk, was just a fuzzy patch. That's all you could call it. And the same is true of this galaxy, which is called M51. We all know about spiral galaxies. That's what we are fascinated by when we look at the Hubble pictures. But these two galaxies actually would have been mostly indistinguishable to the astronomers looking through their telescopes. Well, not quite indistinguishable, because there's a big difference here. This one kind of looks like a plate face on, and this one kind of looks like a plate edge on. And Kant puzzled over that fact and suggested that the fuzzy patches were actually aggregates of single points, stars, too close together to be distinguishable by the human eye. This is the small angle problem that plagued the proof of parallax, and this actually predates the final discovery of parallax. So it was all about angular measurement and resolution. It was only a question of the projected angle of this dish that made the things look different. They might look like plates face on, and sometimes they might look like thin plates, thin lines on the sky like plates seen edge on. He called them island universes, Milky Way-like galaxies made up of billions of stars, just like our galaxy was. These conjectures implied, as we now realize, that the universe was larger by a factor of 1 trillion compared to the universe of Copernicus, which was already much bigger than Aristotle's universe. That means that the volume of the known universe was a trillion times larger than the universe of Copernicus, an incredible stretch of the imagination. You can imagine that no one wanted to believe this. Kant had nothing more than the logs of the observers, who were just curious people trying to document what was out there. The same information was available to everybody at one time. There was no great new wealth of data that Kant had privately. His ideas stimulated many to search for proof, because this was only a concept, just like Copernicus's idea that the Earth moved around the sun was a concept. It was 175 years before University of Chicago graduate Edwin Hubble, building on facts accumulated in ever-growing abundance by hard-working astronomers, anxious to know what was out there, that finally proved Kant to be correct. Again, the heat was intense. Virtually every American textbook in astronomy at the end of the 19th century asserted that the entire universe was contained within our Milky Way galaxy, where we reside. An imagined universe smaller by a factor of 10,000 than Kant pictured. Even with general relativity, Einstein's universe was only 30 times larger. Kant's was the first great leap of imagination as to how big the universe actually was. As it became realized that the speed of light was constant, enormous ages of objects in the universe were implied, because if they're at a great distance, it took a finite time for the light to travel. From 1800 to 1990, the age of the universe grew from 6,000 years to 14 billion years, which is another story. It's easy to see from my repeated use of time spans of about 200 years that the dawning of truth, the so-called the way it is now, and the progress towards it was painfully slow, largely because at any one time there were things that could not be known. 228 years to prove the prediction of parallax, 200 years for telescope optics to mature, 175 years for Kant to be proven correct about the size of the universe. These long times allowed for great feats of technology, not at all driven by astronomy. Let's see, I've lost a slide here. In 1845, Lord Rosse of Birr Castle in the bogs of Ireland completed the challenge to incorporate all of the best improvements of the last 100 years in telescopes into one great telescope, a 72-inch telescope diameter mirror called Leviathan. Adequate cameras were not yet developed, so there are no pictures of the telescope, but one can appreciate the technology of the telescopes by looking a bit further into the structure of Leviathan as depicted in this drawing. The telescope, like the transit instrument on Calton Hill, mainly pointed straight at the meridian and could only be moved up or down. Stars or galaxies were caught as they passed by. The telescope could be moved sideways a little bit by helpers on the walkway, this structure here in the front, which could be positioned to let the observer keep his eye on the eyepiece, which I'll show you in just a minute. You can't appreciate from this picture, but if you actually go there, you see that the walls of this structure are parallel to the highway, or the lowway, so the people couldn't see what was going on inside. It had to look like a castle, so it wasn't too extreme for the people in the neighborhood. Now, as these telescopes got bigger and bigger, there were new requirements that were not part of the early developments in astronomy. The mirrors, as they're moved, tilted one way or the other. The weight shifted on the mirror, and the mirrors actually flexed by thousands of millimeters, but still they flexed enough to disturb the images and make them even more blurred than they were from the aberrations. An engineering company used to making very precise equipment, led by Thomas Grubb, produced a structure that prevented the flexure of the mirrors. This is a system that Grubb built for a 30-inch telescope. You see it had sets of triple mounts, so that, which in an engineering sense would keep the weight even across the mirror no matter what its tilt was. This was a great development. Rosse had to use this for his 72-inch, where the problems were even bigger. This is a picture, you can see the supports underneath the mirror, of a 36-inch mirror that was his precursor to the 72-inch. Lord Rosse, the wealthy amateur, was able to pay for all this, and he polished the metal mirrors with his own equipment. These are modern pictures, which my wife took. This one is similar to the one I showed you in that wonderful sketch made in around 1850. You can see the walkway here where the astronomer stood. The telescope could tilt up and down, and the walkway rode up and down on these ladders on the side, and you could walk all the way across the top of the telescope. This is the eyepiece. This was a particular layout of telescopes developed by Newton. Newton had a little telescope, and if you tried to look down on the mirror and have it focus into your eye, of course your head blocked the telescope. So there were lots of ingenious things that had to be done to get the head out of the way. But the simplest was to put a flat mirror at the top and divert the light out through this eyepiece. I think this eyepiece was probably actually built by William Herschel, the great astronomer of the millennium, probably, who had some incredible ability to make excellent eyepieces. And now, from the backside, you can see the inside structure of the walls and all the ropes and pulleys that were necessary to move this thing up and down, move it slightly sideways, and then on the walkway, the astronomer could walk back and forth. So you could only observe an object for maybe an hour or two as it crossed the meridian, then you had to wait till the next night. The problem was that in this part of the country, I mentioned bogs, there were probably 10 clear nights a year. It was a bit of an arduous project. Still, with all this structure and all the pain that it must have caused him, he was, of course, a very wealthy man, it did turn out to be extremely productive. I'll take you back to my picture of M51. Lord Rosse looked into his telescope and made this sketch, which was quickly distributed throughout the scientific, intellectual culture in England. And you can see that it is not a bad representation. The faint fuzz, the faint red fuzz on the right can't be seen. This is a picture from the Sloan Digital Sky Survey. But there are two nuclei. You can see the spiral structure and so forth. Well, this was mysterious. This had not been expected. I mentioned that Galileo's telescope I did not mention, it was only a factor of 2 larger than the light, it only gave you twice as much light as the human eye could catch, but that factor of 2 changed the world. The Leviathan was twice as big as the telescope of the great William Herschel. Herschel could not see spiral arms. Lord Rosse could. And the reason is that your brain has a hold time of a 16th of a second. If it goes to the next 16th of a second, you can't add the images together. So you needed a telescope of exactly this size to discern the subtle spiral structures. The second amazing factor of 2 that changed the world. Astronomers didn't quite know what to make of it. Vincent van Gogh seemed to. The astronomers still took 85 years to figure out what the spiral structure meant, and in fact to figure out that these galaxies were outside the Milky Way. But this is Van Gogh's painting, which you all recognize, the most famous painting in the world probably, Starry Night. And, you can see the idea that he took from the picture that was circulating around the intellectual circles, the coffee shops. And it's probably the inspiration for these wonderful spiral arms. Leave that up for a minute. Now, my second story of telescopes is a little bit different, but it's still a story of heat. And this time, the heat is from friction because people wouldn't move. The British government had agreed to build yet another of the world's greatest telescopes. And they put together a committee of all the great men who had made the advances of the previous 50 years, some of the astronomers who had been doing the observations. And this committee was to design a 48-inch telescope that would far exceed the properties and qualities of all the other telescopes. Thomas Grubb, the man I mentioned a while ago, Sir John Herschel, son of Sir William Herschel. His role was to advocate that they not build telescopes in bogs. Lord Rosse, other famous names in astronomy, Naismith, Airy, and so forth. Unfortunately, the project was aborted because the Crimean War broke out and the British funds were needed for other efforts. Gold was discovered in Victoria, Australia, and by 1865, there was money to put into some big project that would make the governors of Victoria famous, and they chose what came to be known as the Great Melbourne Reflector. When the committee got together again, the consensus was that no progress had been made in the technology. Of course, you can guess that the people who had made progress were not on the committee. For instance, Lord Rosse saw his tarnished metal mirrors used in this telescope, even though Foucault had built 31-inch mirrors of glass that had silver coatings, were much more efficient and much less consumptive of maintenance time and money. The leap to 48 inches was regarded by the committee from 31 inches as being too risky a leap to make. As another example, Lord Rosse's wife, a portrait photographer, had her own darkroom on the site of Lord Rosse's telescope when the Leviathan was built in 1845. Film, of course, that film was very slow, but improvements were gradually made, and over those 15 years, regular solar photographic patrols of the sun were made by 1860. But in 1865, when the Great Melbourne Reflector was finalized in design, it had provisions for no instruments other than the very limited human eye, the same eye that had helped develop the mists that existed before Galileo. A photographic camera was put on the telescope only in the middle of the 20th century, long after they became standard equipment on every telescope around the world. I call this story Ashes to Ashes. The reason is that Thomas Grubb's son took upon himself to cast the mirror. There was so much metal. There was so much metal that had to be melted that the building caught on fire and completely burned down. In fact, the son climbed the top of the building and threw the embers off so that the mirror would still finish. Okay? The whole telescope structure burned 130 years later. You may have heard about it about 15 years ago. It only accomplished one thing in its life that was of note: a search for dark matter as low-mass compact stars. They were looking for stars between us and the nearest galaxy to pass in front of a distant star and brighten it up because of gravitational lensing. The machos were not found, which was very important because it meant you needed another explanation of the dark matter. Well, the moral is obvious. It's best not to have an old committee if you want to build the next big thing. As I said, big advances came from major advances in technology developed for other purposes. Astronomers themselves sometimes had a hard time actually applying the new techniques in the best way. The march to the very large instruments of today then took a smooth and predictable path in the hands of professionals funded by wealthy benefactors and foundations with little direct government support until the accident of World War II. While progress on optical telescopes continued, particularly under the guidance of George Ellery Hale, founder of the Yerkes Observatory of the University of Chicago, it was gradually found that one actually needs telescopes or equivalents of many different types to gather all the messages coming from outer space. Applications of new technologies to various commercial needs led to the accidental discovery of other kinds of radiation from outer space. There are numerous types of such radiation: ultraviolet radiation, infrared radiation, X-rays, gamma rays, all now observable from space because of the technology of World War II. Radio astronomy developed thanks to the efforts of Bell Laboratories, not to scientists. And particles coming from space were discovered. They're called cosmic rays. For the first 300 years of the revolution kicked off by Galileo, only optical photons were collected. The first of these discoveries of what are called multi-messengers were the cosmic rays. This is a German named Hess, who was disturbed by a lot of background radiation in laboratories that was affecting equipment with electronics. And he wanted to know where that background came from. He got himself a balloon, took up an electrometer. As he rose, the flux of these particles seemed to decrease, but at a kilometer, they started to increase again. And it was obvious that these were particles coming from outer space. This is over 100 years ago. We still don't understand where those particles come from or how they're formed. In 1926, Robert Goddard was doing experiments with rocket. There's now a famous space center named after Goddard. Other amateurs, Germans, were far ahead of him and others around the world. The Nazis adopted that technology and built rockets that could fly hundreds of miles and carry very heavy payloads. The military machine had a need that drove the development of commercial rocket industry. Bell Laboratories, doing experiments in the 1930s, led to the discovery of radio radiation from space, an accident, again, of a search for an explanation for background radiation that was hindering the development of commercial applications, in this case, communications equipment. After the war, the rockets that were developed in Germany and the men who built them, and women actually in this case, were brought over to the United States, and used to implement a space astronomy program where you would launch a payload, small payload. You get 5 minutes of viewing above the atmosphere so you could see photons that could not get through the atmosphere. Then they would come down to the ground and you would develop the film. Well, not always. This is a friend of mine, Ed Jenkins, looking at the broken rocket and the broken film that went with it. He would have had to wait a year to try this again. So this is a very, very slow process. But it did lead to developments that ended up allowing the building of the Hubble Space Telescope. In the late 1960s, people became used to these pictures of big rockets on gantries. This is the rocket that launched the Copernicus satellite, which was mentioned earlier, into space in 1972. And of course, the rockets just kept getting bigger and bigger, leading to the space shuttle. One example, since we're in Swift Hall, is this gamma ray satellite called SWIFT. In the 1968, made public only in 1972, bursts of gamma rays were discovered coming from space. They were found by military satellites. The military satellites were on a mission to answer the question, if we try to monitor nuclear bombs tested underground using gamma rays with satellites, what background are we going to see from space? Completely objective question, no science involved. Right? And the answer was, they found one nuclear test going off every day. This was highly suspicious, and it turned out these were cosmic events, which again are still not understood. But to try to understand them better, several satellites have been launched, one of which is the SWIFT satellite. Now, of course, astronomers embraced all these new developments because they realized that the electromagnetic spectrum, has a tiny slice that we call optical radiation, what your brain can sense. But there's a vast realm of other photons which reveal other amazing parts of the universe that were completely hidden. The development of these new windows on the universe led to the discovery of completely unexpected things you've heard of, quasars, pulsars, and so forth, and the actual first detections of black holes. The black holes were creation of minds back in the 1930s, including by Chandrasekhar here at the university, and men working around the bomb project at Los Alamos. But they never could be confirmed by data. There was no convincing evidence that black holes existed until X-ray astronomy was developed through this, the growth of rocketry. Well, I said they were welcomed, but that's not quite true, because of course you have a culture of astronomers who have had a 350-year tradition of working with optical photons. Right? Optical photons, the equipment that would detect them, and so forth. So for instance, when the idea came up of building a $1 billion Hubble Space Telescope, for many good reasons, people balked. There was amazing heat over this, there were congressional hearings and so forth. Finally, humility won, and a great new universe emerged. I did a poll a few years ago of about 30 well-known experimental astronomers to find out what they thought the biggest development in astronomy had been over the last 400 years. Every single one of them said it was computers. You all recognize, well, some of you may not recognize this slide rule. When I was a student, people wore these on their belts. The bit rate was rather low, but you could do a lot of things with them. They were developed just 20 years after Galileo built his first telescope. But other things happened in commercial technology that set the stage for the slide rule to disappear. This is called the Hollerith machine, which laid the basis for IBM. Punch cards were used to store data and to process data from big projects like the census. Okay. Where did the punch cards come from? Anybody know? They didn't create that idea. there may have been a countess, but they came from the rug weaving industry. They used punch cards on the shuttles to make repeatable patterns that could be sold. So again, here's astronomy benefiting from the commercial developments, and no astronomer ever thought of using punch cards. By 2000, the Pentium 4 chip was developed. The bit rate of the slide rule and of the punch cards was, of course, very low, thousands of bits per second. But this had gigahertz clock speeds. It was smaller than a penny, and it allowed astronomers to suddenly truly build simulations to match with the data. The computers now run our telescopes. They allow us to reduce all the data, which I'll say something about in a minute. And they allow enormous simulations to be made of billions of particles acting under Newton's laws of gravity. This is regarded as the most advantageous development in astronomy, and it came from technology, unpushed by astronomy. The last product of all this technology development was modern detectors. The chips that were used to build the computers led to the development of little devices called CCDs. You have them in your cameras. They make up almost all of the small digital electronics that you see. And the amazing thing is that they have 100 times more sensitivity than photographic plates. This means that an astronomer with $3,000 could build an 8-inch telescope in his backyard, or her backyard, right? Put a CCD on it, and have an instrument just as powerful as the 200-inch telescope at Mount Palomar. That was the biggest telescope in the world from 1948 to 1978. The cost to astronomy was almost nothing because all the development was done for the sake of commercial interest. Of course, if you take that factor of 100 and you put it on a 1,600-inch telescope, like the GMT, who can imagine the increase in knowledge that's going to come from that, which is only a few years off? Who knows what modern ideas will fall by the wayside as new facts are revealed? The serendipitous path of technology development mainly drove astronomy through facts, not speculation or sound theory. Facts acquired through the use of technology, largely developed for commercial and military purposes. Of course, genius, speculation, and sound theory played the role of allowing the facts to be interpreted. Newton, Kant, and Einstein have already been mentioned. But they were reacting to and dependent on the observations to be proven right. I've given you several examples of new things in the sky, the gamma ray bursts, supernovae, and so forth. Some of these may be unfamiliar because they're historical in nature, such as the spiral arms of galaxies. I have shown some examples of new phenomena in the skies that continue to force the rethinking of our view of the universe, why it works, and how it formed. Most of you know from popular magazines the dramatic discoveries that have rocked our world over the last 40 years. The discovery from radio technology of the radiation from the Big Bang, the accidental realization that there is dark matter in the universe, the accidental discovery that there's dark energy in the universe, and the accidental discovery of Earth-like extraterrestrial planets in great numbers. The latter was expected by many, but no one thought to look, even though the equipment we had was quite adequate. The result of all this, all these new developments, which are unexplained, is that the material of which humans are made is now thought to make up less than 5% of the total mass energy of the universe, and our standing as unique beings in the universe is very much open to question. We know from history that we are limited in our attempts to acquire knowledge of the universe. Among other things, we're limited by the surprising and unpredictable technology developments on the ground, by surprising discoveries of new phenomena in the sky, by our ignorance of the right questions to ask, and by our lack of funds for better instruments. Once discoveries are made, some things slowly become understood, such as the nature and constitution of stars. It's taken over 100 years. In fact, it's about 150 years. But as we discover new things, because of various accidents in many cases, we realize that major questions are not being answered that are also very simple to state. For instance, why does the proton have the particular charge that it has? Why is it the same charge everywhere in the universe? And why, well, is it exactly the same everywhere? Was there a time when it had a different charge? These questions are not currently knowable. Is there only one universe, or are there 10 to the power 500 universes? The last absurd statement comes from the idea of multiverses, which I'm sure you've all heard of, stalled right now by the very fact that there are not yet any observations to allow them to be proven, just like black holes, and just like Copernicus's idea that the Earth moved. Many fear, however, that this is an idea that may be correct, an idea as shocking now as was Kahn's hypothesis about the size of the universe in 1755. And of course, as I'm sure you're anticipating, there's plenty of heat over this. You wouldn't believe what people say about each other. Of course, science is replete with much smaller mysteries as well. Smaller, but no more solvable than the large issues discussed above. I can add a personal note to the story along these lines. I am on a lifelong quest to understand a problem called the diffuse interstellar bands, which I'm sure none of you have heard of. Unknown absorption features in stellar spectra, shadows of the creation of the universe that permeate the vacuum of interstellar space, and are no doubt tied to the unknown nature of dust between the stars. The dust that I already referred to that you see in the sombrero galaxies. It's likely that model-independent answers to explain the identity and origin of these hundreds of features are decades away. For the 92 basic elements, the stable elements in the periodic table, the explanations were largely filled in by 1899, that is, the relationships between the different elements. And yet, over the next 100 years, we gradually unveiled the presence of 600 completely new features, each of which seems to arise in a single separate molecule, 600 new molecules that don't exist on Earth. I have personally always been confronted by our ignorance of nature and the universe, and am most appreciative of the fact that I have been allowed and paid to pursue something that is intrinsically interesting to me, but of little apparent practical use at this time. Allowing such pursuits is the hallmark of the University of Chicago. We can only be humbled by the grandeur of the universe and our ignorance of where it actually came from and why it is as it is today. Despite the heat of the battle and the arguments, most scientists are brought, I think, at one time or another, to a point of humility and awe at the puzzle of the universe in which we live and breathe and have our meaning. I am brought to this point by realizing the extent to which our understanding is the result of the accidents of technology driven by non-scientific forces over the last 400 years, during which the knowledge gained from telescopes has so completely changed our view of the universe, its size, its makeup, its origin, and its future. Thank you.
Minutes for conversation and dialogue. Should we keep the lights down or bring them up? What do you prefer?
Well, I have some extra slides, so somebody asked the right question.
Very good. We'll keep it at twilight. So, the floor is open.
Now that we know of thousands of planets going around other stars, Of course, we don't have big enough imaginations to think about what all the kinds of forms of life could be. So we go looking for things that would support life as we know it on Earth, planets that have water. These have been hard to find, but now there are many of them that are gradually being discovered. We don't know the answer to your question, but we expect that over the next 20 years, we will know. And the way we will know is by doing a very subtle experiment where we look at the atmosphere of those planets in absorption as the star passes behind the planet for vice versa. And you can see then the water, the CO, whatever the molecules are in the atmosphere. So this is something that we hope to, of course we won't know the form, we just will know that there are processes that are producing oxygen, or CO and so forth. But this is not that far away. This may be the only example. I gave you lots of examples of things that took 200 years. The gamma ray bursts are going to take that long, I expect. The diffuse band will take that long. Life may not take that long. It's rather surprising.
I'd like to ask a question about whether you think over time the definition and realm of science has changed. Both, I want to extend back a little further to Plato, that in the Timaeus, for example, he is engaging as a philosopher in issues of the size of the universe and using the apparatus that he has to do that. And that apparatus includes the category of myth. That the philosopher uses myth as one of the pieces in the toolkit to think about this. And so in that sphere, cosmology and science in relationship to it has multiple partners. And I wondered if one of the side plots of your narrative is that science emerges as having a particular magisterium that it now must claim for certain kinds of questions, or whether or no it's always been the same, and especially around, obviously, the category of cosmology, which any of us who study ancient religions or even contemporary religions, is a category that people from other domains engaging in speculation and about. So the role of science hasn't changed over time in the midst of cosmology.
The answer is yes and no. And I'm glad I'm not in your class. It's quite a question. Myths, while not made to be disproven, can usually be disproven. Astronomy, with the invention of the telescope, actually started what we call modern science. Soon after the telescope, the microscope was invented, all the work in biology could be started, et cetera, et cetera. So that was a major shift where science did have a new meaning. And you could ask Chris questions in the laboratory, and you could answer those questions. So that's what we normally think of as science. You ask questions, you get answers. First you get money, then you get but of course in astronomy we can't do experiments like that. All we have is our minds and the accidental discoveries of observers. So to cut this a little bit short, interestingly, we're back to Plato when it comes to issues like the last questions that I asked. Why does the proton have a certain charge? That's not a question that we're even close to answering. That's the realm of higher physics, which is gradually merging with astronomy. Astronomy is gregarious, it's trying to take over all. And it's out of that kind of question, which is not being answered by the big accelerators, which are the largest things that will ever be built in public money. That means that you're kind of at the end of answering real questions. for lack of an answer, new myths have been created. And one of those myths is the multiverse. And I mentioned that there was a lot of heat about this, and the heat is over the question of whether this is science or not. Can we really ask this question? Because we're so used to 400 years of asking questions and getting answers from experiments. But how do you tell if there's another multiverse? You can't even see into another universe. So there's enormous heat with this. And gradually, over 20 years, physicists have started getting prizes for this kind of thing. Not the Nobel Prize, but the Berkeley Prize and so forth. So there's a gradual increase of thinking, as I said, that this can't be right, but it just might be right. And this is striking fear into the souls of many famous physicists. So in a sense, we've come full circle. Yes?
What does dark matter not look like? Yes.
What does it not look like? That's a wonderful way to ask the question. The only property that dark matter has, which we understand, you can't see it, smell it, taste it, feel it, is that it has gravitational forces. So it moves things around. And if you see a galaxy moving faster than it should normally move under Newton's laws, then you know there is dark matter. That's basically the argument. This was first found in 1968, has been confirmed over and over again, and interestingly, now no one even tries to build models, real models of galaxies in the universe without sticking with dark matter. Nobody knows what it is. It's one of one of the biggest approximations that is made in modern science. Everybody agrees with what assumptions should be made, but it's an example of something that after 200 years made us overlook because it was a wrong answer.
You speak about the elements or the majority of technology within coming from commercial and military origins. What do you think of the current shift of commercial ventures towards explicitly space-minded ventures?
Explicitly what?
Or, like SpaceX or other
firms
that are trying to take on that?
They'll probably find things about rockets that NASA never would have found because they're asking too specific questions. Their goal is to make money. So I think it's fun. And it's clear that NASA, it was very successful. With 2 shuttles out of 125, pretty much the predicted failure rate for such a complicated mission. But it stopped the whole industry. Now we have no shuttles. And so I think it was a smart move to put it into industry. Because then if you fail, you lose investors, et cetera, et cetera, et cetera. So I think it's fine. I should say that I feel, and many people feel, that once you've done things in space, you can learn how to, after all, make observations from the ground that are relevant. So I actually think of space as a short-term experiment that teaches us how to ask new questions, which we can then ask from the ground. So I don't think this is at all negative for astronomy. It mainly has to do with NASA's mission is to expand the influence of mankind in the universe, which is not a scientific goal. And to that end, the commercialization is great. I just don't want to buy their socks and find out.
So someone with this kind of humility but amazing grasp of an infinite, some part of an infinite reality, and yet finds a role to go to church on Sunday. Do you find, are you a model that we could hope for of putting these worlds together? Can we look to the scientists of your time who does both? as a kind of model of a new kind of piety?
Giving a talk on humility is a little bit hard to answer that question. Thanks to Bill Rossi for that joke. You know, one might like to think so, and there are plenty of people who are humble. What bothers me is not that question. It's the question of all the forces on the other side, demanding irrational behavior, ignorance of what is happening to the earth and things like that. So it's not clear that if there were an army of humble physicists just asking what's going on out there, they would have much effect on the world, because right now it's so dominated by strange politics, which I really don't understand. As far as the intellectual side, the books that are written in university workers, sure. But I've never heard, you don't see, it's like Calvin saying, you know, he's got plenty of work to do, he'll never die. You don't hear people talking about that, because we're all working on solving things before we die. So having my attitude that let's look at history and realize that it took 200 years for major advances. And these new surprises are likely going to take that same amount of time. Certainly opens up questions about divinity, about the Creator, and so forth. Whether that can ever influence society, I don't know. It doesn't, I mean, in a sense, it doesn't matter to me, because I feel the way about things that I feel about it. And I don't hear it talked about very much, so it's a very good question. You should answer. I will say that in the class that when I taught, or in fact, you did get this right, except you didn't get Bill's out. I should have had him answer the question. I think we had about 50 students over 2 years, and I think students were pretty impressed that maybe the views that they were bringing, from family, from history, and so forth, needed to be re-examined. That was the feeling I got. We saw it in their papers and so forth. So maybe if there were more discussion along these lines, it would have some influence.
Is the answer that the humility of the scientists ought to carry over into a new kind of humility in the religious sphere?
Yeah, and I would say in the political sphere.
In the political sphere.
Because we have this fight about what can science tell us about the Earth and about the atmosphere and what's going to happen and so forth. And in many cases, you discredit science, you discredit, sorry to be political, you discredit the government activity and so forth. But so it's true both intellectually and in the political sphere. And yes, I think it should. In fact, I don't see why people are so brash and adamant about their views. It's just not justified by the history of having about the information. We're not responsible. It just happened.
Do you find that the requirement for astronomy as a science to be an observational science, do you find that that impacts the way you think about science and the scientific method as opposed to science that happens with experiments in a laboratory?
We don't think much about the scientific method. And the Draconian story is not the way things happen. It's just like everything else that happens because of people's passion, because of prejudices, which they just refuse to give up and find them and maybe proven right or wrong. But the scientific method has little to do with it. I didn't have time to tell you the shocking story of the moon, the pictures of the moon, Galileo drew. There actually, you could not have the pictures that he drew actually existing at one time. He was emphasizing the features that he wanted to emphasize, namely the glinting of the sun off the mountaintops, beyond the line of the daytime. where the meridian was, the angle and so forth, were drawn at times that could never have actually existed. So all scientists do this. We can't help it. We get so sure that we're right that we go ahead and superimpose our views. So that's just part of it. Now, to be more direct, the story that I was telling should have led you to think that observations are really the prime need. This is behind the Sloan Digital Skyscraper, which I didn't talk about. But that's a 2.5 meter telescope, and I'm talking about 20 and 30 meter telescopes. In an age when you're building little big telescopes like that, this little telescope had to do a survey, and this was how they were felt at the time, to actually take a new census of the universe to find out what's out there. All of astronomy, I'd like to say, until 2000, was done with samples of 100 objects in different categories, quasars, pulsars, etc. It's too small a sample. It's like going to a national NCAA basketball championship, standing at the back door, watching all the players come out and judging humanity by the size and the talk of those players. So now we have samples of millions. Some things have been confirmed, some things have been completely accepted. It's a necessary step to just stop and look and listen a little bit. Now, not to say, as I tried to counter, that intelligence and genius and so forth are important. That's where we get the interpretation of the new data, which doesn't make any sense. But without the data, you're missing what the universe is like. And without the data, we don't know. So there's still plenty of stuff to be observed. Observers should not go away. Besides, I am an observer.
So, I would like to invite you to join me in thanking Professor York for you have honored us with a really fantastic and rich talk that we will remember and continue to talk about. We have a reception downstairs, and this is a polyglot reception because there are multiple people in Smith Hall today. So let me just tell you who you are in case you wonder. There's the usual folks who are here all the time, like the faculty who are here and students. There is, as introduced at the beginning of the talk, the Baptist Theological Union Board of Trustees. There are also prospective students to the Divinity School who are here for our fall open house meeting. Some of you have on name tags, but some of you are unmarked by this point in the day. And then downstairs there's a reception that is hosted both by the Dean's Office and by our Divinity Students Association. So who knows what awaits us downstairs, but certainly excellent good conversation to come. So thank you everyone for being here, and we'll see you downstairs in the first floor commons.
We thank you for listening to or viewing our podcast. For more information and for other podcasts, please see our website, divinity.uchicago.edu/podcasts. Copyright, the University of Chicago Divinity School.